PLC Size and Application. The way that PLCs are categorized depends on a number of things. The main thing is inputs and outputs, the cost, the size, what sorts of things they can do, but the main thing is probably I/O count. That's the number one most important size factor and determining thing that separates the various classes of PLCs from one another. Now, some people would say that a nano size is anything less than 15 input and output points combined, followed by micro, which was 15 to 128, medium 128 to 512, and then large is over 512. Not everyone agrees on those breakpoints or those names, but certainly you have to have enough inputs and outputs on a PLC to work with whatever machine it is that you want to automate. Now, very often what you'll find is that you'll think you only need a small number of inputs and outputs, and when you start building the machine you realize that to make it work you're going to need a whole lot more sensors and a whole lot more output devices. So it's always very important to think ahead with the PLC and just leave yourself some room for expansion. Now, when it comes to PLCs, the way they're used in application, there's three basic categories. There's single-ended, multitask, and control management. Now, single-ended is probably the most common type I've seen. It's where a single PLC controls one machine, one assembly line, one entity, one thing. There's nothing else trying to control that line. Now you might have, the PLC networked or something where you can talk to it. It might communicate with other things, but the point is that that one PLC controls essentially one whole machine. A multitask PLC is a little different. It's a PLC that typically is large, but it actually controls multiple machines rather than just controlling one process. Probably calling it a process would be better, but you can think of it as one machine, or in a multitask PLC, the PLC controls multiple machines. Now, there are advantages to doing it this way. A lot of times PLCs are fast enough and processes are slow enough. There's no point in wasting the processing power of a modern PLC on one menial task, right? It's better to use that PLC, slap on a couple more input-output modules, and let it take care of a bunch of machines at once and minimize cost. Now, that can cause problems down the road, but often a system is set up so that the machines that they work in tandem with one another, and it's a whole system anyway, but made up of individual machines. So the dividing line between a multitask PLC and a single-ended PLC can be a little bit blurry, but typically this would be typified by a PLC that has a lot of inputs and outputs. So this is a significant factor in this type of application. A control management PLC, on the other end, is one where the PLC controls other things. So you might call it a master PLC. It's a PLC that communicates with other PLCs and computers, and there you may or may not need a whole lot of input-output points, but you typically need a PLC that's very fast, has a lot of speed essentially. Its processor runs fast. And basically it supervises other PLCs, tells them what has to be done, when to go. Maybe you have one PLC that controls just a small machine, and other machines being controlled by other PLCs, but one master PLC that tells all those slave PLCs, if you will, what to do, when to do things, and how to work together. So again, the lines can be blurred between these because you might have a machine that there's one PLC controlling most of the process, and then you only have one other machine controlled by a separate PLC. So you've really got two single-ended PLCs talking to each other, and that's about it. The main thing that differentiates this from the other applications, the key is communication, that there's a lot of electrical communication going back and forth between the various devices in order to work together and make things work properly. And typically in this kind of setup, the master PLC can also do a lot more than just communicate information to it really has control over the other PLCs. Memory, as we've talked about in a PLC, is a part of it, and when you're selecting I/O points, that's the obvious thing that you need. The other thing that may not be obvious is selecting how much memory is needed. you're probably used to having a computer set in front of you that at least has 4 gigabytes of RAM. When I was a kid and I had my first computer, it had 64K. It was a Commodore 64. 64K, well, that's a thousandth of 1 megabyte, and a megabyte is a thousandth of a gigabyte. So you've got 4 million times the memory that I started off with, roughly. No, not quite that much. But anyway, the point is, you expect computers today to have just scads of memory. PLCs aren't necessarily that way. PLCs still often are measured in kilobytes, or more often today, megabytes or even gigabytes of memory. Now, megabytes is more common. I haven't seen a whole lot of gigabyte, but I'm sure they're out there. I don't do this every day. In our regular language, we usually talk about kilo being 1,000, but in PLC and computer language, kilo means 1,024, and the reason for that has to do with the base 2 system that all PLCs and computers in general use. We'll look at numbering systems a little bit later, but the other thing that's a little bit different about memory, especially in a PLC, is that 1K could mean 1,024 bits, it could mean 1,024 bytes, which a byte is 8 bits, or it could be 1,024 words, where a word is 2 bytes. And so it just depends on how the memory is, specified for that particular manufacturer as to what 1K of memory means. Now, the amount of memory you really need depends on how big of a program you plan to write, how many I/O points you have, because the more I/O points, the more memory you need. How much data you want to store in the PLC. Maybe you need to collect data. Maybe you're running a machine where you're making widgets and every widget needs to be measured. If you make 1,000,000 widgets in a day, you're going to need enough memory to store those 1,000,000 points of data, or you're going to have to go in between and download it or something. Another thing that is important to consider when deciding how much memory you need in a PLC is future expansion. How much, what might be added on to this later, where we don't really want to buy a whole new PLC. Also, how much communication has to be accomplished. The more communication, the more memory that's required. That's just part of communication. So all these things play into selecting how much memory goes into the particular PLC. Now, the card that's being shown here is a fairly old card. You can see that it's made to plug into a backplane. There are backplane connections indicated on the left-hand side, and there's a battery backup on the right-hand side. Now, that battery backup is a dead giveaway that this is a pretty old PLC. Flash memory has become more common these days, where the memory can be changed electrically. So you just write your program and it stays. You shut off the system, the program's still there, you turn it back on, it's still there, no problem. Kind of like having a thumb drive, That type of memory was not all that common in the past, and so battery backup was used so that if the power went out, the memory still had enough power to maintain the program and the data and so forth. Now, you will still find PLCs in industry that have battery backups, and those batteries have to be checked from time to time and replaced. Probably the most common type of battery used are lithium batteries, because they're such long-lasting batteries. They hold a heck of a lot of energy for their size. But they're more expensive too, and with any battery, eventually it's going to run down. Lithium batteries are not rechargeable types. Am I thinking? Yeah, I'm thinking of the right type, lithium battery. So today, modern PLCs, I don't know of any modern PLCs that include a battery backup because of flash memory, but older PLCs, you see this is an Allen Bradley SLC 500, affectionately known as a Slick 500, and they were a very common PLC in the past. The instruction set is all the commands that particular PLC supports. And there's really a set of very common commands, and then each different PLC commonly will have a different set of commands beyond the regular. So there's the examine on, or examine, it's XIC, examine if closed. That's the instruction that I've been showing you, where it just looks like a switch. Then there's the XIO, examine off. And all that is, that's the set of contacts with the line through it. Okay, so those first two instructions are things you've already seen in ladder logic. Now don't worry, you don't have to go into the program and type XIC when you want a set of contacts. You just drag the instruction over into your code and use it. Now OTE is output energized. When I showed you the brackets on the right hand side of the ladder logic, or the circle, the coil, that's what that instruction is. It's an OTE instruction. It's non-retentive. What that means is that the ladder line that leads up to it can turn it on and can turn it off. Now there are also latching instructions, and then there's timer instructions and counter instructions. What you see here are what you're going to find on, every single PLC out there. And then on other PLCs you'll find more instructions. For example, the XIC and XIO instructions basically allow power to pass when what they're sensing is high or low. Sometimes, and in fact very often, it's very beneficial to have something come on when there's a change from high to low, a transition, a so-called rising edge when it goes from low to high, or a so-called falling edge where the signal goes from high to low. Maybe you want something to happen when a switch is pressed, not just based on the fact that that switch is being held down, but when the switch changes state, you want something to happen in your program. That is a rising or a falling edge. And so Automation Direct, for example, has instructions in their palette that look like the regular context in XIC, but it has an arrow pointed down or up to indicate that this is a switch that turns on when it detects a rising edge or a falling edge. So each flavor of PLC ladder logic has its own subset of commands, and often there are more commands than you really need and will often use. But here are the ones that are very common and you're likely to find in every PLC out there.